Hello Reactor enthusiasts, this is a second part video for the numerical background modeling of the WWER-1000 simulator. In the previous video I tried to prove my hypothesis, which is the model doesn't take into account boiling in the primary water. After dealing and fighting with a lot of rod withdrawal, insertion and boron concentration, I could not prove my point because I didn't have enough available reactivity left in the rods that were not inserted, and I could not conclude anything in that video. I decided to do the second part, in which I thought a bit the strategy before starting the simulation, and meanwhile we see this image here. This is a WWER reactor construction in Rostov nuclear power plant, and here we see the hexagonal pattern of the fuel assemblies before closing the reactor vessel. Okay, let's go to the simulator. We will start with okay, just with the normal 100% nominal power. Okay, start the simulation, and now my idea is to decrease primary pressure until we reach boiling. So I will monitor power and see the state of the group 10 auto control and see how the reactivity is affected. So we go directly to the primary circuit tab, and I will just turn on the water spray in the pressurizer. This will spray cold water into the steam. This will make the steam condensate, and this will decrease the power in the primary because this pressurizer is connected, if we follow this line, with the primary, with the reactor. So let's open the valve TK40S09, open, and let's remove the auto control of this variable valve and set it manually to some values, more or less 3/4 of the maximum aperture, maybe a bit more, we'll see. Now we are at 160 bar more or less, and it's decreasing fast. Now we'll see as these automatic heaters turn on. These are electric heaters, so they receive energy from the electrical grid and heat up this water as we introduce cold water inside the pressurizer. When the water starts to decrease, because we are just showering this with cold water, they will start turning on to keep this temperature at a temperature not too far away from the primary temperature, which now is at 317 degrees. This is at 344. Okay, now they just turn on the 4-in-1s. And I will select, probably will have a look into the 3D plot. This is the relative power. Okay, I will not look at the relative power, we are not dealing with that now. I will look at the reserve before boiling. We have 19.63 degrees now. And the most critical part is the center annus here. I'm not sure if checking the central rod or this perimeter, like 2 rods away. Probably I will check this perimeter. Yes. So I will take this rod here, select. What about this? 19. Okay, so this fuel element here is 19, and this fuel element here, it's also 19. Is this working? The central one is at 20 from boiling. This one is at 19.7, and this one is at 19.2. Okay, so this is the most critical. These 6, which also contain control rods, but actually now the control rods are totally withdrawn in this group, which is group 6. So it's the same as if they were not here. Pressure decreasing 155, and now I will need to go to the tab and disconnect some securities. So first of all, the security, 150 bars for power above 75 degrees. And I will also disconnect this, but probably will not need to go as far as 140, we will see. But I just disconnect just in case. What else could we need? I think with these two we'll be fine. And probably we'll disconnect automatic control to just look at the reactivity once we reach boiling. 18 degrees now. I will just... Okay, we have the pressure warning here, but that's normal. That's the point of this we are doing. I will just increase the discharge of this valve to accelerate this. Now it's at the maximum, almost maximum. Okay, maximum discharge, and the pressure is going down. We're at 154 now. Let's look at this. This plot, we'll see that the red line in the plot below, it's the pressure, it's going down slowly. Now it increased the slope a bit because I just increased the discharge of cold water showering. And this cold water comes from the TK. It's actually the valve in the primary TK40S09. It's the same in the TK display here, TK40S09, which closes the loop. If we follow this loop, no, it's this way, like so. It goes through this thermal exchanger, and then it goes to the 1C here. If we click here, we go to the other tab. And the pressure is almost below 150 now. Let's see how we are. We're at 17 degrees of boiling. And I will now probably disconnect the ACP, or maybe wait a bit more in case there is some drift in power. Okay, I will disconnect it. Let's see. Theoretically, there should be a decrease of power because we're increasing. Well, no, we're not increasing heat, so I'm not sure what should happen to reactivity before boiling. I will not say anything because I don't know. So just have a look into the neutron generation. The plot looks stable. And the pressure is still going down. We're at 150 now. 16 degrees to the boiling point. So just to remind, because I didn't explain everything I explained in the previous video, this is to prove that the model doesn't account for boiling in the primary. If the model did account for boiling, when we reach the boiling point in some of the rods, reactivity should go down very sharply, because this pressure water reactor, boiling creates a negative void, so it means we're creating voids into the moderator, which is the water. And because we have less moderation, we have less reaction, and the reaction will go down, and we will have a decrease in power. This is the contrary of what happens in RBMK reactors, like the one in Chernobyl, in which we have a positive void. It means when the cooling water starts boiling, we have a positive increase of reactivity, because that water is not moderating the reaction. It's the graphite that moderates the reaction in a RBMK reactor. So this is a very interesting and useful security feature, having a negative void, because it means if for any reason reactor goes wrong and the water starts boiling, for instance with a lack of cooling, the reaction will just go lower and lower just automatically, because this decreases the moderation of neutrons. The same, I can say the same for the RBMK, but the contrary, it's a very unsafe situation having a positive void, because when things go wrong, suddenly the power starts to go up very quickly. Okay, we heard some blinking. This is the pressure going below 150 bar in the primary. We see 149 now. And the reserve before boiling is 15.7 degrees. And everything looks stable. Power, offset, everything looks stable except the pressure, which we are purposely decreasing in the primary. I'm hesitating about disconnecting these heaters. Maybe if I disconnect them, the pressure will decrease more quickly. Let's see. Probably yes, because these heaters create some boiling, so they counteract the effect of the cooled showering. I will disconnect 3 of them. Just leave one like in normal operation. Why the number 2 doesn't want to disconnect? Okay, now I just disconnected all the heaters in the pressurizer. Let's see the plot. And yes, we got a faster decrease of pressure. That's good. Let's see if there is some alarm for the temperature in the pressurizer. TP, it doesn't seem so. Temperature 1 higher than something. DT S1 2 higher than 75. I guess this is between 2 legs. No, it is between primary and secondary. Okay, that's totally fine. DT in the primary less than 10. Just in case, I will disconnect the security. Just in case, but I don't think. I think it's between 2 legs of the primary, not between any leg and the pressurizer. And the other things look fine. Okay, we're at 13 degrees of boiling, and the power is still 99.8. So almost, we just have a very slight decrease, but that's fine. And we've got a TK disbalance. So, should we do something here? Okay, let's just open this valve here. So this will feed some water because we are feeding water into the primary from the circuit. The circuit is going low in level, I guess. So this will level up this tank, the TK10B01 from the TB30B02. Pressure at 141, and we're at 12 minutes of simulation. Reserve to boiling it's 11.8 degrees, and the shape of the reserve looks the same because the power, the relative power, is essentially the same. So what should we expect to happen when we reach boiling? If boiling was accounted into the numerical model, we will see a decrease in power in this highest area. So maybe we should write down some values. I will do it now. In the central area, which is the one involving the fuel elements of the group 6, is at relative power. I will just write down the absolute, not the relative, of 23.62. 23.62, and then there is a plateau in the rest of the reactor with peaks at 21.58. Okay, and I will just write down the minimum at 11.37. So what we expect to happen is to see a decrease of power in this higher plateau, the one of 23. and see the second plateau at 21.5 to be essentially at the same level. Probably if there is a decrease in reactivity, because this is a reactor with a chain reaction, a decrease in any part will cause a decrease in all the reactor. But of course, if you are decreasing the reactivity in this area, the decrease in this area will be much more acute than the one is creating in the surrounding areas. So we expect to see some decrease in all the reactor if there is boiling, but the first and higher decrease will be in this area here. Let's go back into the reserve before boiling, and we're at 9 degrees now. I will just withdraw a tiny bit rods to keep power 100% because it went down by 0.1%. We see here in yellow the rod position, and we see in red the neutron power, which just went up a tiny bit. And I will put this into scale. Scale by limits. IC. Good. We see a temperature in the pressurizer 332 and the temperature in the primary 317. So still very hot in the pressurizer, even if I have all the heaters turned off. Okay. Just 7 degrees to boiling. No more alarms triggered, this is good. And for the moment, just waiting. Essentially, the physics of the reactor is still the same, the neutronics, because the water is still liquid, so we don't care too much if we are at 6 or at 20 degrees from boiling while the water is liquid, because it keeps mainly the same moderator properties. So we see the reactivity at 0, still at 0. Six degrees. We are getting closer and closer to the boiling point. I will readjust again. Scale by limits. Which one was it? The RC? Oh, no, what's the RC? This is the secondary. So we have a very sharp increase in secondary pressure. Okay, just because I scaled it. But actually the variation is between 60.1 and 60.0, so it's fine. It's the IC I want to scale. Okay. Still decreasing at the same rate. And the pressure now it's 130 in the reactor, 129 in the pressurizer. Why this differential? Because now water is flowing from the reactor to the pressurizer. And you may say, why it's flowing? If it's water, it's incompressible. We don't have gas here. That's because of the elasticity of the structure, pressure structure containing the water. So the pressure vessel, primary conducts, and the pipes going till the pressurizer. This is made of steel, and steel will dilate or contract depending on the pressure inside, and this will cause a small variation in volume that causes some flow of water in this pipe, which I assume it's a very small pipe, because in normal operation it doesn't need to transport a lot of water, and that's why in this case we are really forcing this thing to go to a very low pressure. We have a very high discharge here, and we have losses because of Bernoulli in the conduction. That's why of this pressure differential 127.62, 126.8. Okay, we're at 3 degrees from boiling, very close now. Let's have a look into the secondary. Everything works totally fine. And everything looks fine also in the nominal values for power, neutrons, offset, and everything. Just look at the power. This is the relative in absolute values, still almost the same as when we wrote down values a few minutes ago. We're at 2 degrees from boiling. Very close now, reactivity is still 0. What did we get now? Okay, luckily we connected this or disconnected the security, otherwise we would have a scram now. Okay, that's very good. So happy to have disconnected the security. So DTS1 less than 10. Let's see why this happened. 1726. It seems there is a temperature in the primary. I thought maybe it was referring just between 2 legs, but no. It seems that this is referring to, let me check all the legs. Wait, here it's very high, this 86, 16. Okay, because between the cold and hot legs. But yes, that was referring to all the primary, including pressurizer. This means that if the temperature between pressurizer and reactor or any of the legs of the primary is higher than 10 degrees, or better say the hot legs is higher than 10 degrees, this will create a scram. So well done disconnecting this. Should I disconnect something else? For the moment, no. We're at 2.2 degrees of boiling. Wait, this increasing? Why is this we have a pressure, the power decreasing now. I will withdraw rods. Okay, we're at 100 point something. 1.8 degrees from boiling. 120 bars in the primary. It's crazily low. And we're at 21 minutes of simulation. I need to keep withdrawing rods to keep at nominal power. That's strange. Okay, be careful, I just went up to 101. We're at 1 degree from boiling. Let's look at the 3D plot. So the power output looks to be still fine. The reserve before boiling, it's almost touching the 0. We're at 1 degree. I will... That's strange. The reserve before boiling is not really going down. I will withdraw a bit more rods. We are 1 degree from boiling. Let's look at the 3D plot. Let's continue withdrawing. We are almost with all the rods withdrawn. and we're at 116 bars. Very low pressure in the primary. We're with all the rods withdrawn at the maximum position, and we're still at 0.9 degrees from boiling. Not yet boiling. Let's see why this is happening. Now we have that the reactor is at a higher pressure than the pressurizer. This means that the water is flowing from reactor to pressurizer, still like before. I will just put into scale this, scale by limits, I see. We see the secondary circuit a bit like crazy now, but this is a very unmeaningful scale, so it doesn't matter. We see the power slightly going down. I will just use boron decrease. I will disconnect the boron exchange model and go to the boron shim into manual mode and decrease boron. And I'm in nominal power again, and the reserve before boiling is still 1 degree. And let's see the absolute power. We still have the same value at the top, 23.60 something. And we have some distortion here because we have been moving rods. I will keep decreasing boron. I will try to go a bit farther from the 100% nominal power, but no more than 102, because otherwise I will create some alarm. Okay, and the pressure is really low now, it's 111 bars. I wonder how is it possible that we still keep decreasing pressure and keeping power, and we don't see relevant changes anywhere in the 3D plots. Now it really seems that the reserve before boiling is getting closer between this region and the high activity region. Let's decrease more boron. This value here in this rod is still not at 0, but very close. I will decrease a bit more boron, but I'm afraid I will end up with this video without a strong conclusion. With the data I see, I cannot really tell if the model accounts or not for boiling, because what I expected to see is as I increase reactivity with boron, I increase this plateau here, while I keep this at the same value because the boiling doesn't let it go further. I'm not seeing this for the moment. I mean, I see the same shape as before. We got all this region without reserve before boiling. It means we should already have boiling in this region. And I'm able to increase power without increasing the level of this plateau with respect to this level. So if I should say something according to the results is, I think boiling is not implemented into the model, but the result is not really, I cannot say this with a big confidence. Now here we really see that the reserve before boiling is getting close to zero in all the reactor, not only in the central part. And I think from this is the evidence that I was looking for. We are boiling in this area and we are not decreasing reactivity. So let's see what happens when all the area of the reactor reaches this level, but I think this is the evidence that boiling is not accounted for in the model. Decreasing boron once more. And now we have all the reactor boiling. We got a reserve of 0 in all the reactor except these corners here, that in which we still have a reserve of 7 degrees, which are these cold rods. I will just select one of them. We have 7 degrees in this particular rod, but if I click anywhere else in the reactor, we will have 0. Like here, we have 0 everywhere. So what are the conclusions we can extract from this experiment? Now we have boiling in all the reactor. We have this power profile. So we could say boiling reduces reactivity across all the section, but we compensate this with boron decrease. So at the end, boiling plus boron decrease leaves us with the same situation according to reactivity, and we will still have the same layout according to neutronics of this reactor. But what I expected is, as we decrease pressure and this central area is affected first by the boiling, we'll see a decrease of the reactivity of this area, and we'll see this equalized by this other between this and this other plateau. We didn't see that. That's what makes me think that boiling is not implemented. And now we just got a scram because the level in the steam generators is below 22. We have a low pressure, we have a lot of alarms. But I think what caused the alarm was the low pressure in the steam generators, the low level, or the set point. Let's look at the graph. No, it's not the set point because the power is going low. Level in the steam generators are these 3 lines here. I don't see why. I'm not sure this caused the EP. For sure none of these 3. Level, pressurizer, I think it could be this, the level of the pressurizer. Well, I'm neither sure about this. So, well, it doesn't matter too much what caused this scram, because we were running the reactor in a very unusual condition. So now I'm not sure what caused the scram. Maybe this? What's the green line? 1213 or 213. I don't see if there is a 1 or not before the 2. This seems to be the level in the pressurizer. Yeah, yes, this is the level in the pressurizer, and this could be the reason. Here it touched, here it went down, went up, it went down. Yes, exactly. So it's this level in pressurizer lower than 400, and I didn't pay attention to that, so that's totally possible. And why this happened, maybe because of boiling. I cannot really tell why, but for sure the level in the pressurizer went too low here, went below 400, and this caused this scram. We see the decrease in power here a bit after the level went below 400. We cannot analyze anymore these outputs now because the reactor is shut down, but according to what we saw during the decrease of power of the primary, I would say with some level of confidence that the boiling is not accounted for in the primary model, nor physically, so it's not accounted in the thermohydraulical exchange model, and nor in the neutronics model. So that's my initial hypothesis, and that's my conclusion. Not 100% sure, but I'm like 80% sure of this looking at the data outputs. And if someone has some opinion about this, you can just tell me in the comment section. Okay, thanks for watching. See you in the next video. Bye.